All right then, so welcome to day 3, and thank you for being here one more day. I promise this is going to be even shorter than yesterday. Yes, so we got two practice today. But I'm going to start anyway because I have to introduce a new concept, a couple of new concepts, so that practice can be completely understood. So let's see what we did today so far. So we learned what modal symbolic learning is. We learn what modal symbolic learning is by placing ourselves on top of propositional symbolic learning. So we introduced what do we mean by learning logical formulas at the propositional level and then at the modal level. We formalized how we are able to learn in the particular case of supervised learning, and which is one possible way to do learning. So one thing that I said at some point is that if we are able to do decision trees, it means that we have learned something, we have understood something about the entire framework, and therefore everything else should come a little easier. It's quite easy to do random forest. It's quite easy to interpret the formulas. It's quite easy to do everything that is around. This is exactly what we're going to do today. Again, focusing on the supervised case. We understood that defining modal decision tree is not easy because we want to keep correctness, completeness, and efficiency of the method. And then, so what happened is that our model decision tree, look like a little hard to understand. So it took a while to interpret these objects just like this one. At some point, I said, okay, if we want to learn these kind of things, we have to generalize the idea of splitting, and in particular, instead of splitting just among two possibilities, well, instead of splitting among all the possibilities in which two children can be, we have to split among all the possibility a subtree can be, and subtree can be quite long. We have to check all possible back edges, and then we have to check all possible forward edges. So on paper, this looks just as easy or as hard as it was in the propositional case, but then in practice, we have to compromise a little. So what it is this very first part about is what do we mean by compromise? Now, I want to stay here for a second and ask you guys whether or not this is what we would like to learn. And now, okay, let's say this is too much for a moment. So what should we give? What should we get rid of? What should we give up for a little while? Of course, if we start eliminating parts of this tree, eliminating features, characteristics of the tree, we're going to lose completeness. But as I said yesterday, the whole machinery can be dialed down and up as we want. So the point is, how do we dial down? So what do we do? So what do you think it's reasonable to do? Is it reasonable to say, okay, don't look for all the atomic decisions? That we lose. In that case, we would be losing all some of the propositional power. So no. Are we able to interpret the formulas even if there are no backward trees? Well, backward trees allow me to build more formulas. But if I didn't have backward edges, if I didn't have backward edges, would it be the case that I cannot interpret the formulas here? No, I can still do it, only I don't have enough expressive power to build all of them. Therefore, if I just say, look, in my implementation right now, don't look for all possible backward edges. Just, use self-backward edges. And of course, among all your possibilities, there won't be the entire range of formulas, but there will be maybe enough formulas for some problem. So this is our first idea now. Let's say we don't use backward edges just for now, and see whether or not we can learn, we can still learn. What about forward edges? Forward edges, let's see if we have an example here. Forward edges, we said they modify here. They modify the flow of decisions, right? They modify the flow, how the instance falls on the tree. But again, in some of the nodes, there are no forward edges. In general, forward edges are self-loop, so they don't modify anything unless it is necessary. So in the original algorithm, the one we saw yesterday, I have to search for all possible forward edges in a certain situation to see whether or not the flow of decision, to see whether or not modifying the flow of decision makes sense, and it gives me a better local decision. And so what happens if I say, okay, don't look for forward edges? And again, the tree is still a tree. Formulas are still model formulas. The tree is still correct. It's not complete anymore. I mean, the family is not complete anymore, but the tree is still correct. And of course, if I argue that it was efficient before, this must be even more efficient because I have less things to worry about. So here is the second idea. Let's give up, just for the time being, backward edges and forward edges. And of course, I can learn less things. I can learn less concepts, but they're still model. The formulas are still maybe still meaningful. Okay, let's see one other problem. Okay, let's go back just for a moment here. This is an example, we said yesterday, this is an example how formula can look like. Okay, if you had any experience at all in modal logic, you would say these formulas are not all equally easy to check. What did I say day one, hour one? I said, your first take-home message is efficient model checking is something that you cannot not have. You cannot give up if you want to do this, if you want to do any symbolic learning at all, in whichever language. So our algorithm is build the formula systematically and then check it. And then we said, look, unlike the case in propositional logics, in general, building new formulas could mean building formulas that have nothing to do with the formulas that we have built so far. Therefore, every time is a new model checking instance. So now we need to be efficient in model checking generic formulas. And then the observation is these formulas are not all equally easy or hard to check. Why? Well, because some of the formulas have no alternations of quantifiers, while some other formula do have alternation of quantifiers. And then I call Sasha and I ask him, is it the same to check formula with or without alternations? The answer is no, because the more alternation you have, the harder is it to check it. All right? Of course, if I use the same model checking algorithm, the model checking algorithm, the classical model checking algorithm, is unaware of that. So the computation, the complexity is the same. Okay, and on paper it doesn't look very much complex because it's just look for in every world and then label every word with the smallest subformula that you have to check, and then build your way up. So at every step of the way, you got to look at every word and label parts of your formula on the word, whether they are true or not. So why alternation of quantifiers have a role here? Because it is natural to think the other way around. It is natural to think, okay, if I've got my instance, remember my instance of many words, I check the formula true here, and then I check the formula diamond true to see whether or not I want to go here or here. It would be natural to see, all right, diamond true is true, so give me the witnesses of this truth, of this truth. So the one, the successors of the word what I am into, and this is everything you need to know to keep on checking your formula. Now, if the formula is completely, if the alternation is 0, so you go, for example, on this side, then what happens is that you only have to keep trace of one set of words at every time in order to check the rest of the formula. And this is computationally very, very efficient. Otherwise, if you start going left and right and you start producing formula like this, then hypothetically, the data structure that you gotta keep is something like, it's a multi-set like this. First the set of witnesses, then the set of witnesses for each one of them, and then the set of witnesses for each one of the level before. So this structure gets more and more complex at every step of the way, which means that if I want to use a different algorithm for checking these formulas, and I want this to be particularly efficient, what I would like to do is to limit the alternation of quantifiers. Limiting the alternation of quantifiers means even further reducing the expressive power of the tree, but this is what it is today about. So reducing the expressive power, well, we worked so hard to get it, and now we're giving it up. Why? Well, I said it before, and I'm going to say it again. I want the complete system so that I know systematically what I want to take off and put back, take off and put back as I want it. Okay, so it's a different story than I got something that works, and whether or not, I don't care if it is complete or it is not. So what he's going to show to us today at the beginning is one case. So it is the current implemented version of the model decision tree, the currently implemented version, and this currently implemented version is somehow dialed down in the sense that I try to explain just now. So let's see. Let's see what we have here. Let's go. Let's start. Oh, sorry. Are we here? So let's start with day 3 then. Okay. So this is our original definition. We know this already. These are the conditions that tells everything we need to know about backwards tree, backward edges, forward edges, and these are the definition. This is exactly the same definition we had yesterday. How do we change it? Well, we said no more backward edges function. We got backward edges function, we got forward edges function, but we want them somehow reduced. Now, we want them reduced in order to obtain 2 objectives. First, we want to reduce the quantifier alternation, and well, basically that is everything we want. We want to reduce the quantifier alternation, and we want to keep the fact that the entire tree is correct. So we want to keep the fact that we always know what to do. So we modify these conditions, and we put some other conditions. Now, it is not really useful to go see the details of this condition. We got the idea. The idea is please produce only formulas that have, let's say, 0 quantifier alternation if we can now. And let's see whether or not, what can we achieve, how can we achieve this? Oh, there is one other thing. The other thing is, we already knew that splitting on diamond true and box false looks good on paper because it allows me to build all the formulas that I want, and I don't have to enrich my vocabulary, okay? Remember, we got the propositional vocabulary, and we just add in 2 very small atomic modal formulae, so that we could build all of them. But now we are in the real world, and splitting between diamond true and box false in the real world, it gains basically no information. Why? Because it's very hard to find a situation in which I'm on a word without successor versus word with successor, and hope that this has some information about the class. It could be, but it's statistically very unlikely. So what do we know? Well, we know that if we had the forward edge, then we could look ahead a little bit. So we could split at least with diamond P and box not P. This already makes sense. There is an interval in the future with fever, with average fever. Now we can use the correct terms now. F of fever, whatever it is, average, maximum, number of peaks or whatever. So there is an interval in the future with that condition about on the fever that true or there isn't. It's completely different than saying there is an interval in the future or there is no interval in the future. Okay. The second has no information. This may have some information. In order to achieve this, what we do is use forward edges, which we want to get rid of, but okay, we use it in a very, very limited way. So forward edges can only exist on top of a diamond true. So now what I'm building here is diamond P versus box not P. So this subtree here is equivalent to the subtree with only 2 children, 1 root, 2 children, box P, diamond P, box not P. And you should say now, why didn't you start this to begin with? But if you have understood anything, you know that theoretically speaking, I can't, because I gotta work much more to put all this together. So I know I already have a complete tree now. I'm only trying to make it useful now. So I'm doing this unnatural thing to get something very, very natural, which is splitting on something that I hope it has information. There it is. Okay. So now these conditions, what do they say? They say first, only diamond to the right and boxes to the left. Why? Because I know that this is going to give me less alternation. It's going to give me no alternation at all. Second, forward edges exist only in these situations. Backward edges only exist in order to make this situation possible. And now I can have an idea. I can have a definition of what we can call restricted model decision tree. Restricted model decision tree look like our old model decision tree. They have less fancy things on top of them, which make the formulas easier. And as you can see, they have no quantifier, no alternation of quantifiers. Now, why do we check diamonds also on the right? Well, we check diamonds on the right because if we go to the right here, then you know that diamond P is false. And now the next things you want to check is whether or not diamond S or box not S is true. So again, you check a diamond. So basically, at every step of the way, you check a nested diamond formula. And checking nested diamond formulas, it's much easier than checking every formula. What is the grammar, the context-free grammar that you get from this? This was our old grammar. This is our new grammar. Now, because this is complete, now this one must be a fragment of it. It may not be clear to us immediately, but it is a fragment on it. Of course, the way we build formulas is very restricted, as you can see here on the left of the implication. We only have propositions, sorry, literals, and we have a very restricted way to build formulas. But this is exactly what I wanted to. I mean, I've got a method that can learn any formula. Right now, if I implement it in that way, it may be not as efficient as it should be to deal with real problems. I don't want to wait for that. Let's dial it down a little bit and see what happens. Now that I have a restricted decision tree, what I can do is put it in the real work.